Staying awake, and right, I want to tell you about two ideas that have come up from a consortium that I'm part of. Is ultimately funded by the US Navy, by EPSRC and the DSTL here. And the point of this consortium is not to find out about human vision, though I'm one of the human vision people on the consortium. They're mostly computer vision, machine learning, reinforcement learning people, and the US Navy would like us to come along and tell them how to do reinforcement learning better. Okay? We're going to talk about adversarial networks again, as we had in the session this morning, and that's one of their key focuses. They say this is unacceptable. You show, like the images this morning, I'll show a school bus, which is classified as an ostrich, and they just say, go away and sort this out. And so I'll just talk about a couple of ideas that relate to that. And mainly I'll talk about policies, and I'll explain what that means. I think there's it's something familiar in reinforcement learning, but it's something that the emphasis today has been on how we produce a vector, a state vector at the end of a neural net, and it's actually what you do with that and go on to the next state in a robot that's moving around that I think is important and has important implications for how we think about what the brain does. So thank you to the people who are involved in this. I will mention very briefly experiments that we're doing in our lab, but I won't focus on those because it will take away from the main discussion that we're having here. And theoretical work goes some with James Staliker now, with Andrew Fitzgibbon, and in fact from way back with Miles, who's in the audience. Yeah, and it's funded, as I say, by EPSRC and DSTL. Okay, I want to start talking about evolution. This is a pretty simplistic version of evolution. Okay, and I'm going to go even simpler. I'm going to say there's really only two important things that change in evolution. And you're cleverer than I am, so you probably say that the two things that I'm talking about are correlated, so it's more like one. But anyway, we'll start simple with a bacterium, and this bacterium has cilia, okay, which can either waggle or not waggle, okay? But the important point is it can do that in two different contexts. So it will have four policies. So it can waggle or not waggle when the bacterium is small, and that, it's crucially, should depend on the gradient of sugar that's around. This is in a hypothetical world. It's a good example. And then it could waggle or not waggle when it becomes large. So it absorbs plenty of sugar, it's nice and large, it's ready to divide into two, and now it's looking for some other chemical B, in the environment, which will, when it's absorbed enough of it, will allow it to divide, and then it starts again. Okay, so that's the life cycle that we're considering here. And the important point is there are four policies, and there's a current state. The current state is composed of its mass, the gradient of sugar, and the gradient of this other chemical that's going to allow it to divide. Okay, so we can draw it in 3 dimensions quite happily. This vertical dimension is mass. This dimension coming towards you is sugar, gradient of sugar, and that dimension is the gradient of chemical B. And I've coloured the 4 different policies, so this is not waggling versus waggling, or not waggling versus waggling, but under these 2 different conditions. Sorry, the dark is not waggling, the bright is waggling. Anyway, and so we have a state vector. At the moment, it's large and it's waggling because there's a gradient of chemicals, so it's good that it does that. Anyway, you get the idea. We can tile this sphere with different policies. Policies are not actions. Remember, it's only got 2 actions, waggle or not waggle. Policies are the contexts in which it interprets a state and says, okay, I'm going to choose that action. Okay, that's what the policy is. So this is evolution. We started at the bottom. There's a 3-dimensional state space, 2 actions, 4 policies. Great. Now, the good thing is we can zip pretty quickly up to the brain. Because the front half of the brain, roughly, tells you about this thing, which in the bacteria is telling you about its internal state. It's nothing to do with the outside world. It's what its state is. which in its case are just big or small. In our case, it's many more things, whether you're hungry, what your current goal is, etc. It's pretty complicated, a pretty big bit of the brain, but it's telling you about, ultimately, what your goal is, what your task is, what you should be doing next. Nothing about the outside world. And the back half of the brain roughly tells you things about the outside world. And we're just going to say that is your state vector. That you put those together, that tells you what you should do, what your policy should be. Now, go up the evolutionary scale. We've not got to brains yet. We've got plants. They're clearly doing quite sophisticated things on the basis of different sensory states. So they have a wider range of actions, certainly a wider range of policies. So this is how neural network action is pi of s. That's the policies. Actions are a function of the state. And so we've got the current state, and it is moving around this state space with all the coloured patches of the different policies, and that's successful. Note that if you attach the wrong action to the same policies, the bacterium would die. If when it was large, it waggled its cilia in response to the sugar gradient, and when it was small, it waggled its cilia in response to the chemical B, it would die. Okay? So these policies are linked in chains that are successful. And if you go from one policy to the next, to the next, to the next, you will survive. Okay, humans, we've kind of done them. So more policies. The point of this video is not all policies lead to an overt motor output. You don't have to move. Someone's sitting there for half an hour thinking about whether to move the pawn to e4. Well, there's lots of policies, and this state is moving around. We're now much higher dimensional space, but conceptually it's the same kind of thing. With this state is moving around as you're thinking about whether to move the pawn to e4. Neural nets, that's what today's about. They obviously fit in this little gap here. So this is an example from Abhinav Gupta's group that I really like. It's a quadcopter learning by disastrously crashing into walls how to fly. Okay, and after a mere 12,000 trials, it's pretty good. This video on the right, it's if you wait long enough, a person will come out of that door and it will avoid them. So it's not just learned where the chairs are, it's learned the rules about how to avoid obstacles. Okay? It's pretty impressive. And that's in the same framework. There's 3 motor outputs, go left, go right, go straight forward. The state space is, in this case, happens to be 1024 dimensional, and it's learned the policies that will get it to move around that corridor and not bump into things pretty successfully. So that fits in there. Often you're working in 4096 dimensional space. That's very popular. But anyway, it's the same kind of thing. And presumably, by this logic, you push that further. You go to higher dimensional spaces. You have more policies. That's all that we really need for higher intelligence. So, compared to what Tim was saying, too simple, too complex. I guess the criticisms will come in, this is too simple. But anyway, that's an idea I would like to push as a good model for what the brain is doing. You know, the brain's a useful mechanism for generating a lot of stored feature vectors, a lot of stored policies, and we're good as we wander around the world at our state space, moving around this space. But it's not that hasn't happened all the way through evolution anyway. There's nothing particularly miraculous about our brain. Okay, so neural networks concentrate a lot on the details of what happens. All I'm saying is at the end you get 4096, a 4096 dimensional feature activation vector, the current state, and that moves around. In neuroscience, we again concentrate on this bit that's giving probably higher than 4,000 dimensions description of the current state, but it's much the same. I noticed in Tim's brain that he showed us, he left out this bit, which is, I think, probably a pretty important place, the cerebellum, that is anatomically designed so that it can store a vast number of feature vectors, stored feature vectors, in the same dimensionality, the same dimensional space as the firing rate vector, and you pass them all through with your parallel fibers, and you compare them to many, many, many stored feature vectors. I think it's at least worthy of including in the brain.
It doesn't fit as nicely on your desk.
But you're just producing a yellow dot. Right. Yeah, Tim left that bit out. The thing that I'm telling you is very old. This is 50 years old. Okay, as far as neuroscience. So if I'm right, neuroscience died. Neuroscience was over in the 60s. Okay, and now you guys are coming and taking this tool. You're doing amazing stuff with exactly the same operation, and now you're flying quadcopters and everything. Okay, so just a quick glossary because people might pick me up on this. This is from the same paper that Charles mentioned at the beginning, the Hinton paper in 2012, to say when I draw a sphere and I'm doing nice simple things like saying distance on the sphere, Hinton was describing the same kind of thing. I have made some simplifications, but they're not that wild, is all I'm saying. So the current feature vector is what... So these are the terms that I'm using. These are terms used in neural network papers. There is a relationship between the two. These red dots are the stored feature vectors. These Voronoi cells are the classification. Dimensionality of the space I keep going on about. 4096 very commonly in neural nets, but it's all growing all the time. Number of stored feature vectors, that's the number of classification things we've classified. Number of policies is the same because there's one action per stored feature vector. A number of actions can be tiny. Okay, this, you can have someone completely paralyzed and they can move their eye to the left or right. That's binary action. But the number of policies, so they can write a book with moving their eyes to the left or right. Okay? That's what matters, is your policy space, not the actions. Okay? It's how you map a state space onto an action, 1 or -1. Okay. So this is where I talk about adversarial networks, and you've had a whole session on it in the morning. So, but my message is policies, policies, policies. So if you want to think about image recognition, try and think about the policies that humans would use when they look at an image. So you may have had this particular image. If not, if you've had many similar to this. So the neural network has no trouble classifying this as a bus. Add a tiny amount of the tiny contrast of this adversarial noise. It still looks like a bus, but it's classified as an ostrich. And in fact, all these images are correctly classified originally, but add a little bit of adversarial noise, and they're all classified as an ostrich. Okay, well, you've had that in spades this morning. So what can I add to that? Well, just to say, this is my picture in relation to those spheres that I was showing. This is how I would relate what's going on here. So this is the Voronoi cell, the region, all of which, if the state vector comes up anywhere in this space, it's classified as a school bus. If it comes up anywhere in this space, it's classified as an ostrich. And all you do to get this adversarial noise is to take this vector, subtract them, and you get a difference vector, and you increase this. If you walk along this difference vector until you just get over the boundary, and bingo, that's your adversarial image. Okay, fine. So simple to do. The Navy is absolutely apoplectic about this. brittle, inefficient, inaccurate. Okay, they really, really don't like it. So they would really like a solution, and they'd like the human vision people to come up and say something sensible about it. So this is one attempt, and that's that we don't do it like that. We might see this bit and say, oh, that's the text of bus, and then I'm moving a saccade, a particular saccade, a known angle of saccade. I move them down to here, and I recognise this as a headlamp. And then another one, I recognise this as a wheel, and so on. You can either do that literally with your eyes or with your attention. Either way, you get a set of answers, all of which are the answers you expected because you moved your eye or your attention, and lo and behold, you get something that looks like a headlamp. There is no way on God's earth that you're ever going to recognise that as an ostrich because of the way that you've just done it. You said there's a little bit here, and then I move, and I get this bit, and I get this bit, and I get this bit. Okay, all of which are expected. Policies. And to be fair to the reinforcement, to this machine learning community, they're doing this kind of thing already. They're saying, if I recognise this bit at the centre of a cat with eyes and a nose, I have an expectation that somewhere up here I'm going to see an ear. Okay, and they're using that expectation about the spatial structure of images, and it helps. And that's good because it's bleeding obvious. And they're doing this with videos. So if you see a video sequence of this guy pitching, then this is what you expect to see next, and so on. So expectations that come out of what you're recognising now really help overall. So don't try and do it all in one big bang and recognise the school bus as one set of pixels. Do something a bit more intelligent. So when I said this to the group, they were slightly taken aback, but this means that the neural network have learned entirely the wrong basis vectors. Sure, use 4096, but get them right. Okay? They have got them absolutely wrong if they think this is the set of states that correspond to school buses. Okay? They're the wrong basis vectors. And the question, so the last part of the talk, so how should machine learning learn human-like basis vectors? And I think there's, again, something sensible that one can say about that. So I come over here. So I do a little chat. Right. So compositionality. So Charles talked about compositionality, and I possibly have a slightly different take on it. I'm not quite sure. But anyway, this is what, when I talk to the US Navy people, this is what they talk about. They say, okay, this is one classification. There's a red object in the sea. Okay? And this is another one, there's a cube in the sea. The compositionality problem is, having learned that really well, they'd like to identify the situations in which there is a red cube in the sea. And they can't do it. These are really, really clever guys. Okay? And it's quite staggering sometimes what the neural net community cannot do. So they can learn it again. You could say, all right, well, I want to train this other thing, which is to recognize red cubes. But they're not using this learning or this learning in doing that. That's kind of starting again. That's the compositionality problem as I understand it from them. And the thing that's really important to say as a biologist, a neuroscientist, someone from our community is, well, that thing that you're trying to do is absolutely fundamental to the way that animals learn. They learn about, cubes, and then they learn, but if it's a red cube, I must do something different. It's really critical. So I keep the learning that I've done, and now I split it. I split the categories, and I can apply different policies in different cases, okay, because of this extra thing, that it happens to be red. This is how the face developed. So I was originally a doctor, and we had a lot of this stuff. And it's really striking. So a face is developed out of fish gills. And the embryo, a human embryo, will go quite a long way in developing fish gills before it said, oh, hang on a minute, now I need to make this into a face. No engineer in their right mind would do that. Okay? But that's an aspect of biology. We start with things, and then we change them a bit. And then we change that a little bit, and we change that a bit. And we're sort of forced down a route. So, yeah, this is how a face develops, really quite complicated, but originally it starts with these fish gills. And so the same fish gills could develop into gills or different things in reptiles and birds, and in humans it's face. Okay, and this is how they develop into fish gills. But, okay, what's the relevance of that? I'm going to show you a few examples, all of which are the same pictures, and they're all, you start with something broad, and then you divide the category, and you divide the category, and you divide the category. And they're all things that we know. I'm just saying it's really important, A, and B, the reinforcement learning guys do not do this at the moment, and they really should. So I think that's input number 2 from us to the US Navy project, that we say, you could do something different, and it would be really helpful. So, all of these states are, there could be a predator. Okay, get ready. Okay, so you've got an action. You get more information in. Okay, I'm not quite sure. Definitely, better run. Or more information. No, it's fine. It's fine. That was something else. Okay, so that's how we take information in and we adjust what we're about to do according as more and more information, as our state becomes more refined. Perception, the same. So if you're in 3D perception, you would all know about this classic problem of seeing a disparity surface that's elliptical and you don't know whether it's elongated or flat. It's kind of a bit esoteric, but it's Andrew will know all about it. It's a very familiar problem. Okay, so perception of a space, you could start with this thing, A is in front of B. Okay, that's very broad. Okay, it's quite useful, but it's broad. You get more information, you get the disparity surface, and you say, okay, well now I know I've got an elliptical disparity surface, so I know I can rule out a lot of shapes, but there's still a family of shapes that it could be. It could be circular, it could be squashed, it could be elongated, and I finally get more information, for instance from divergence or other information that tells me how far away it is, and suddenly I know, oh, that's an elongated one, or that's a squashed one. Who cares about the details? The point is, it's another example in perception of how we go from a broad classification to a narrow one. We do this all the time. Okay, we're at the moment doing experiments in virtual reality where you're wandering around a maze, and the best models of what people are doing are that they start off with some vague topological description, and then you get more details about how if I go down that route, then it's quite long, and there's quite a lot of turns, I go down this route. So you add more information about these arms of the topological maze, and eventually you get so much that you get the metric full description. It doesn't matter. I'm just saying we start off with broad descriptions of things, and then we narrow them down and we narrow them down. That's how human learning and perception and representation work. These experiments, because the summary is up the top, psychophysical evidence against 3D reconstruction. So we do a bunch of experiments, and the message is always the same, that when you do things, this is homing, this is you see an image, and then you'll put somewhere else in VR, and you've got to go back to it, and you do modelling of it. The message is the same, it's not 3D, it's something else. The one that I just showed you with moving around the maze, or this is another one where you walk around some screens and then you have to point at objects. The take-home message from all of these is we don't build a 3D model in the head. Okay? And if we had an hour, I would go into the detail of that. But we're talking about neural nets here, and this is some. So if we don't build a 3D model in the head, what do we do instead? Well, this is why I'm excited by what's going on in the neural net community, reinforcement learning community at the moment, because they really are doing it a completely different way. They used to do SLAM, that's geometry, to work out where things are. They don't do that anymore. They reward systems for going from a current image to a rewarded image. And this is, I really like this. So it's from Google DeepMind. They have a set of images going into a network, and then they generate an image from a new viewpoint. So you tell it the viewpoint of these images, and then you just tell it a new viewpoint it's never seen this this scene before, and lo and behold, it tells you what the image is. So it's just like the experiment we were doing, where you walk down a tunnel, then you have to point at some objects. Of course, it's trained on millions and millions of similar type scenes. This is where it's fabricated some things, like these purple things. When it's only got one image, it really has to invent stuff. But when you've got a few images, so it's got occlusion here, it's got shadows, it has no 3D geometry. It's just learning. Okay? It's just learning the relationship between images and locations. And once you've told it with millions of examples, if I give you this image and then I give you another image over there and I tell you the XY location in the room, I can give you a completely new scene, and you can do that transformation. And you're doing that transformation not through geometry, not through trig and sines and cosines, but through learning from previous experience. And that's got to be what we do as well. So this is back to the one I showed you before, just to show you the details. And I'm really saying this is the same as what I've been saying earlier on. There's an atomic unit of action, and it includes the observation, that's the image that's in front of you at the moment, and the target, that's the image that you're trying to get to. And it feeds both of those into a neural network, and it learns a policy, turn left. Okay? And you do that enough times. You saw when it really works 100 million times, that's a lot. But it does learn, in the end, the best route to go from A to B. Yeah, Alex is doing some work on what the feature vectors are like in the high-dimensional space. I'm happy to talk to you about that afterwards, if anyone's interested. But the important point that I want to say is, just like I was saying at the beginning, this has a sensory component, just like the bacterium with the sugar and the chemical B. And it has a motivational component, a thing that's telling you what the task is, something that's only internal, not about the outside world. And that's just like the mass of a bacterium. And it puts them together, and the combination of those, without a 3D map, tells it what to do. So it's just like this. It's a sensory component, the motivational or internal component, and that tells you what to do. And as I was saying at the beginning, well, we got in 3D vision this kind of preposterous idea of V1, posterior parietal cortex, doing egocentric stuff, passing this presumably by some 3x4 matrix to hippocampus, and yada. Maybe it's much simpler. Maybe this bit is giving you the motivational context. This bit's giving the sensory context. Put them together in one vector. Compare that to the bit that Tim left out. And choose. So this is just a long lookup table. What is your current state? Have I seen something like that before? And I'm going to choose a policy as a result. So, we're nearly there. Adding dimensions. So, just to say, for those of you who are kind of awake and critical, I've drawn, what do I mean? I draw this category with a point here, current state, and then I divide it up here. So I've still got the same point, but I'm saying that's in a subset, okay? Well, obviously, actually, what I must mean is to add dimensions. So here's a lower dimensional hyperplane, the grey plane, corresponding to the dimensions of early learning. That's the broad one. And then when you learn more, you have to have more dimensions in order to be able to split this space. So these two are the same when you project them down onto the lower dimensional hyperplane. But they really do correspond to two different Voronoi cells, two different categories with policy 1 and policy 2. Okay, so early in learning, whether it's early in evolution, you have lower dimensions, late in learning or later in evolution, you have higher. And the hypothesis is that you only add a dimension when it's evolutionarily advantageous to do so. So I put in the abstract, you eat green fish is good. But then you may know that green fish with yellow spots on, not good. Okay, so you need a new policy. You need to split your eat green fish category into two. And it's crucially advantageous to do that. So your task space is dividing up and getting more complex. And your state space is becoming more complex only to the extent that it's necessary to divide up spaces and have different policies accordingly. Okay, so just a few examples to finish off of that kind of idea, with always on the x-axis going from a broad categorization to a more specific one. So early in learning, you see that it's coarse. Charles mentioned coarse and fine features as something that's, you know, and global shape and that kind of thing. But if we stick to coarse features, you can act on that coarse feature. You say, oh, there's a face. I'm going to orient towards that face. I'm not quite sure whether it's a face facing that direction or that direction, but I better look at it. And then a few milliseconds later, you're getting more detail. Now you can, it's definitely a face. I'm not quite sure whose identity it is. More fine-scale detail. The action identifies. You know, you can shift your, etc. You've got different policies as the new data comes in, as your state space becomes more and more refined. So it's tempting to speculate that perception recapitulates evolution. And reinforcement learning really doesn't seem to do that at the moment. And that the ostrich and the school bus is an example of it. It's just not doing this kind of hypothesis testing as the information comes in at all. So another example is the same image over and over. You might categorize that as an old pot. As you learn more, you might categorize it as a Delftware pharmaceutical pot. If you're a real expert, my wife is a real expert in this, and it's an 18th century English one. Fine. You know, but it's the same image, but you're doing more and more sophisticated things. You definitely started with a broad category and you're dividing it up. Something that they are not doing. You've seen these videos before, but just to re-emphasize, early in learning, you're in low-dimensional space, and you're adding more dimensions as you're. I'm saying this is a kind of sophisticated version of that. We like the face developing out of fish gills. You start with what you had before, and then you adapt it. Where I don't think the engineers are doing that at all. They're just going blam. Let's identify school buses from all the examples of school buses. There's nothing like that in this learning. Yeah, so people are trying to do this. This is work by Martial Herbert's group and Phil Torr's group, but they're in the really early stages of trying to add dimensions to this is called growing a brain. They're how do you split categories? It's a difficult problem. This is the final slide. We tend to think that the brain does this. The information goes in, comes to the thalamus, goes up to cortex, and then yada, 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 does fantastic things. We pass it through cortex. We can do any kind of magic in the cortex, gets to the motor system, and then we get a motor output. No. So these two people, so Ray Guillory was in the same department in Oxford as me, and Murray Sherman came to visit. The only bit of neuroanatomy I've got really excited about, and it's fantastic. They looked at the thalamus. What happens in the thalamus? Each area of cortex information gets passed down to the thalamus, and a copy goes to the motor output. And then the same thing, you go up to the next area of cortex, and it goes to the thalamus, and a copy comes down here. And when I say a copy, I literally mean a copy. Okay, so here's the picture of the axon coming down, and it splits. The same firing rate is going down this end and this end. One of them goes to the motor system. And they say the idea that information relayed through thalamus to cortex is a copy of motor commands also suggests that our perceptual experiences are built on these commands. Whatever the interpretation, the anatomical fact that many or all inputs relayed by the thalamus are branches of axons that also target motor structures requires some further consideration in a typically understated phrase. I think it's completely mind-blowing. We should really, really think about it. And what it's really saying is the cortex has hierarchical policies. Okay? Information comes in, do something with it. Sure, pass it on, and then that layer does something with it. Motor output. Pass it on, the next one does something with it. And that's where I'm at. So to summarize, evolution, something like that. Concentrate more on policies when you're thinking about recognizing an image, and compositionality is crucial. Thank you very much. And one last thing to everyone who did the work. One last thing to say is we've got 2 postdoc positions coming up and being advertised very soon, so look us on our website. Thank you very much.
Thank you very much. Do we have any questions?
In terms of like a policy for object recognition,